Hello class, in this video we're going to be looking at binary, permutation, communication, and dominance matrices. The learning intention is for us to explore the different types of matrices, for us to learn how to analyze communication matrices and calculate the number of one-step and two-step communications, and lastly for us to analyze dominance matrices and rank individuals in a round-robin tournament. So the first thing I'm going to be talking about is defining what is a binary matrix. As you can see down below, binary matrices are matrices that only contains the number 1 and 0 as its elements. And for a binary matrix, it can either take on the shape of a square or a rectangular array, but I've underlined square because that's the most common form of binary matrix that we see. Now, there are different types of binary matrices that we'll be unpacking in today's lesson. So there are 4 types of binary matrices. One type of binary matrix is called the identity matrix, and this is represented by the letter I. The identity matrix is important because it actually acts as the number 1, like in maths. So whenever you multiply a matrix with the identity matrix, this doesn't actually change the value whatsoever. Another type of binary matrix is referred to as the permutation matrix. Permutation matrices are denoted by the letter P. And what makes the permutation matrix so special is that when multiplied with another matrix, this could either rearrange and shuffle the elements in the rows or the columns. And we'll look at this in a bit more detail later on. Another type of binary matrix are communication matrices. Communication matrices are denoted by the letter C. And communication matrices are used to represent the communications between groups of people. And lastly, another type of binary matrix is referred to as the dominance matrix, which is represented by the letter D. And in this particular case over here, what you're doing is you're showing the wins or the dominances over individuals in a round-robin tournament. In each of these examples over here, all of these binary matrices are square matrices. So that just means that they've got the exact same number of rows and columns. And again, I just want to emphasize that binary matrices are just matrices that contains the number 1 and 0. For the purposes of this video, I'm not going to be talking about identity matrices at all, but I will be covering these 3 types of matrices over here. The first type that I'll be covering are permutation matrices. A permutation matrix is defined as a square binary matrix in which there is only one single 1 found in each row and column. And as I discussed earlier on, we use permutation matrices so that we can rearrange elements found in another matrix. These permutations can either occur in the rows or columns. So what I've got over here is a row permutation. So in this case over here, this is my permutation matrix. And when I multiply that by a column matrix, notice over here, it has shuffled the orders of the elements found in each row. So as you can see, that's why it's called a row permutation. And another example is a column permutation. So in this example over here, the matrix is being multiplied by the permutation. So this time the order has been shuffled around. And when you've got a row matrix multiplied with a permutation matrix, notice that the actual columns this time have been shuffled around, and this has now produced a different word. Let me now explain in a bit more detail as to how these processes occur. So the first type we'll be looking at is a row permutation. Row permutations occur when you've got a permutation matrix, and this is multiplied by a column matrix, and what it does is that it shuffles the rows found in the column matrix. So what I've got over here, as I said, is the permutation matrix, and this is being multiplied by the column matrix. Now, in order to actually shuffle the elements found in a row permutation, you're going to need to follow these steps. The first step is to analyze the position and locations of the number 1 found in each respective row of the permutation matrix. So what I'm going to do now is I'm going to look at this horizontally, and the position of the number 1 found in each row will tell us the row in which it will replace the original element. This part of the second step doesn't really make sense too much, so let me show you an example as to how this occurs. So what I'm going to do is I'm going to look at this individual over here, the first row, and notice that the number 1 is found in the last column, okay? It's found in the 3rd position, okay? So what that means is that the 3rd letter found in the column matrix has now replaced the first row. So therefore R goes into the first row. In the second row, the number 1 is located in the 2nd position. So therefore, this means that the letter A will therefore move into row 2. But in this case at all, this has no effect at all. So therefore, A remains the same. And for the very last row over here, the number 1 is found in the 1st position. So this means that the first letter is therefore moved into the last row. So therefore, the new word that it spells is going to be rat. Let's now look at another example. So I've got another example of a row permutation. Again, I'll do the exact same thing where I'm going to analyze the positions of the number 1 found in each row. In this particular example over here, the number 1 is found in the 4th position. So therefore, this means that P now goes to row 1. So I'm going to put P over here. In the second row, the number 1 is found in the 3rd position. So therefore, A is now shuffled and moved to the 2nd row. For the 3rd row over here, the number 1 is found in the 1st position. So therefore, L in this case moves into the 3rd row. For the 4th row, the number 1 is found in the 2nd position. So therefore, E is now moved into the 4th row, and therefore the last one is going to be S. So therefore, the new word spelled is going to be pails. Let's now look at column permutations. So column permutations occur when you've got a row matrix, and this is then multiplied by a permutation matrix, and in doing so, this shuffles the columns found in the row matrix. In order for us to perform a column permutation, it's going to follow very similar steps, but in this case, you're going to be analyzing the positions found in each column rather than the row. So what I'm going to do now is I'm going to draw vertical lines over here, and I'm going to identify the positions of the number 1. For the very first column over here, the number 1 is found in the 2nd position. So what that tells us is that the second letter is therefore moved into the first column. So therefore H goes first. In the second column over here, the number 1 is found in the 3rd position. So therefore the letter U moves into the 2nd column. In the 3rd column, the number 1 is found in the 4th position. So therefore the 4th letter, T, is now moved into the 3rd position. And therefore the last letter is going to be S. So the new word that's going to be spelt is huts. Let's look at one more example. So what I'm going to do again is I'm going to draw vertical lines. In the first column, the number 1 is found in the 3rd position. So therefore the 3rd letter is going to move into column 1. So S is going to go first. In the second column, the number 1 is found in the 1st position. So therefore E is going to be moved into the 2nd column. In the 3rd column, the number 1 is found in the 2nd position. So therefore A is going to be moved into the 3rd column. And therefore the last letter is going to be T. And the new word spelt is going to be seat. Let's now look at another type of binary matrix. So we're now going to be unpacking communication matrices. A communication matrix shows how many people are able to directly communicate with each other in a communication system or in a friendship circle. When you're constructing a communication matrix, you tend to represent the rows as the people who send the message, and the columns represent the people who therefore receive the message. In a communication matrix, the number 1 would indicate that these two people can directly communicate with one another, whereas the number 0 indicates that direct communications do not exist between those two individuals. So I'm now going to show you an example of how to construct a communication matrix for the diagram or the network shown on the right hand side. Remember, we always use a letter C to denote communication matrices, and as I said earlier on, the sender is found on the rows and the receiver is found in the columns. Now, in a communication matrix, we often have zeros in the main diagonal, and the reason why we've got zeros there is because that it is redundant to therefore communicate with yourself, okay? So that's why we put zeros in the main diagonal. And now what I'm going to do is I'm just going to go row by row. So in this case over here, Vicky can talk to Stephen directly as well as Kathy, but cannot speak to Paul. So therefore, I'm going to put a 1 here, a 0 because Vicky cannot communicate with Paul, and a 1 here. Now I'm going to go to Stephen. Stephen can communicate with Vicky. Stephen can also communicate with Paul, and Stephen can also communicate with Kathy. And you do the same thing for the other rows, and therefore this is what your completed communication matrix should now look like. One way for us to quickly inspect to see whether our communication matrix is correct or not is to see whether there is symmetry about the main diagonal. So this is the main diagonal over here, and as you can see at this particular line over here, you can see that there is symmetry on either sides of the diagonal. In a communication network, we could use a matrix to represent the number of one-step communications as well as two-step communications. So a one-step communication is what we just did earlier on, and that just shows you the direct communications that exist between two individuals, okay? So that's why it is referred to as one step, because it occurs directly. Now, we could also represent the number of two-step communications that can occur between two individuals. So in order to find out what is your two-step communication matrix, all we simply need to do is essentially square it. So that's what C squared means. So if I was to square this matrix using my CAS calculator, this is what I'm going to be getting. And a two-step communication is essentially where you've got a middle person to pass on a message to the target individual. Let me briefly show you how we can actually interpret the values represented in a two-step communication matrix. So let's just use this value over here as an example. So this is saying that there is one two-step communication that can occur between Vicky and this dude over here that starts with S. So I think that was Steven. So that means that Vicky can talk to one person and that person can therefore relay that information over to Steven. And this is the way that you should be interpreting the information given by a two-step communication matrix. And the last thing I want to talk about for communication matrices is that we could find the total number of one-step as well as two-step communications by using the following formula over here. So if you add up these two matrices, this will tell you the total number. So if I add them together, this is what my final answer will now look like. The last part of this video is to talk about domination matrices. So domination matrices are very similar to a communication matrix, but this time around, it's going to show you the wins of the row players of a round robin tournament. So a round robin tournament is where you've got each participant playing against each other just once only. And what is different about a dominance diagram as opposed to a communication diagram is that the arrows only go in one particular way. So therefore there's only one arrowhead, whereas in a communication diagram or a communication network, you had double-headed arrows. And the way that we should be interpreting these arrows is that the direction of the arrowhead points to who the person has dominance over. In other words, who actually lost. So in this case over here, this means that A has actually lost to B. A has dominance or won over C, and etc, etc. And therefore, all we need to do is display the wins in our dominance matrix as shown down below. When we find the sum or the total of the elements in each row, this will tell us the total number of wins or the dominance scores for each player. So what I'm going to do now is I'm going to add up all these values over here in each row, and therefore this is going to tell us our dominance scores or the total number of wins for that respective player. So in this case over here, it's going to be a bit hard for us to therefore rank these individuals. As you can see, there are two individuals who have a score of 3 and two individuals have a score of 1. So what we're going to need to do now is we're going to now need to construct our two-step dominance matrix. So similarly, like a communication matrix, to get the two-step variant, all we need to do is square the first step dominance matrix. So therefore, if I've done this using our CAS calculator, this is what I'm going to be getting. After I've completed constructing my two-step dominance matrix, I now need to apply the following formula to find out their total rankings. So I'm going to add my first step dominance as well as my two-step dominance matrices together, and using a calculator, this is going to be my final answer. Once I've got this, again, I'm going to now find out what is the sum for each row to get their dominance scores, and I'm going to compare their values. The one with the highest score, meaning the highest number of wins, is therefore going to have a higher ranking. So therefore, this individual over here, the person with the letter B in the name, is going to be ranked 1. So in this case, Berger is going to be ranked 1. In this case over here, the individual with the name beginning with the letter E is going to be ranked 2. So therefore, Emma is ranked 2. In the matrix, we could also see that there are two individuals with the exact same scores. So therefore, they're going to have a tie and be ranked 3. So Anna and D are ranked 3. And so therefore, the last person is going to be ranked 5, which is going to be Cass. By now, I'm hoping you understand all the different types of matrices unpacked in this video and are able to construct both communication as well as dominance matrices. This is the end of the video. Thank you for watching, and I'll see you guys again in the next one. Bye.